Hello. This is Concrete Pad. Today we are going through shear stresses and one more concept of that is shear flow. Shear flow. So during the derivation we had that beam, and subjected to a point load at the midspan, and we said that the bending moment diagram would be a linear function, and we took two cross sections at xx and yy. So the element was dx. So this was your differential element dx. So here the loadings were m, and the loading here was m plus dm. So after that you said that from the neutral axis you take some point A at a distance of y from the neutral axis. So during the derivation we had that section as a rectangle. So if you talk about the section if you take the section as a I section, now if you take that section as an I section, we see this in this form. This is some I section. This is some I section. Now what happened that, so you take that dx element, let's say this is the dx element, so this is our dx element. Let's say this is our dx element. Now what's happened that because of the m moment we had that sagging bending moment, so positive bending moment. So because of that we had top compressive, bottom tensile. So from this side we had some compressive stresses of, we call that as fx on that point A. We said that above that area, when we took that area above that point A, we said there is some net fx, and there is some, from this side there is some net fyy compressive from both the sides. So we said that because dm is more in the yy side, so your net force would be in this direction of that was equals to integral dm or y by I into small differential area of dA. So that dA area. So that was your f net, and we said that there should be someone to balance that, and we call that as f shear. So its direction was in this direction. So the direction of shear force was that is a positive x direction. So it's some shear force that was, we said that equals to tau times that's that thickness of this side. We have the thickness. So we said that there should be some shear stress acting on the thickness, bottom thickness, that was equals to b, and some thickness dx of this one. So we said that the area contributes to shear stress equals to tau b dx. That was your shear force. So same manner we are dealing with the I section. So this was along the long axis. We said that this was acting for the longitudinal direction. If this was your z direction, this was y direction, and this is x direction, so we can call that shear stress as, so that shear stress was acting in this direction, so we can call that as, that was acting tau and perpendicular normal to the surface, that is z, and in the direction of x, so we can call it as tau xz. So your shear stress of tau zx was acting. If you show that same on that dx element, so that let's say this is the dx element. Now you are showing that on the top side we have, let's say the point A was somewhere here. Along the cross section you can show that point A here. So above that point A you have to resist some shear in the horizontal, so that would be resisted by the flanges. So we say that is resisted by the flanges. So let's call it as tau zx. Similarly from the other side also, because section total flange, that section of the flange would be resisting that shear force of f shear equals to tau times b dx. So this is dx and this is your b. So your total shear would be resisted by the whole flange of this above the point A. So let's say this dash represents that if you cut those sections internal, there would be some shear stresses developed from the internal of that flange. So we say that there is some that horizontal shear force developed, or horizontal shear stress developed. Similarly, if you take any point B, if you take any point B, let's say below the neutral axis, and there we have there we have tensile stresses. There we have tensile stresses from both the sides, and because the moment in the y direction is more, so we say that this force would be more tensile. So net tensile stresses would be in this direction, net tensile stresses. So there should be someone to balance those net tensile stresses. Or we can say, if you see the tensile direction, we cut this section, we have this those compressive stresses, whereas the net compressive stress was in this direction on the top. If you take the bottom, that below the neutral axis, net tensile stresses would be in this direction, net tensile stresses. From this side we have less tensile stresses in this direction and more tensile stresses in this direction. So for balancing that net, there should be some F shear that's in the negative x-axis direction. So we can show that, also. That should be in the negative x-axis direction. So let's say this one is your negative x-axis direction. So we can call this one as tau times zx. So there is some shear stress tau zx. Similarly, you can have that on the entire flange of the that bottom flange. So we can show those arrows. So this is your that. Similarly from the other side, you can show that also. Let's say this is also tau zx. Now based on that, we have that on two perpendicular planes, shear stress. We have complementary shear stresses. So on the other side we have tau xz. So if you talk about this one, if you take this element, you said your shear stress of tau zx is acting in this direction. So we have this direction as z, top above that, in the y we have this one, and out of the plane we have z-axis, that x-axis. So that's x-axis is this one, x-axis. So we show on this cross section that x is out of the plane. So if you draw outward normal, that is, we can write that as tau x, and the direction should be perpendicular. So we write that tau x z. So there should be some shear stress developed here also. So there should be some balancing shear stresses also here, tau zx. Similarly for the other side also, from the other side also, there should be some balancing. For this part we can have this part, for this part we can have this part, for this part we can have this part. Similarly it goes up to the mid. Then after that from the bottom side also we can show there should be for this part we have this one balancing. Similarly we have for the other one we have this one, and this one. Similarly for this one we have it in this fashion. So we got some flow. We got some flow of the shear stresses. So we got some flow. We got some flow like a liquid is flowing. So we call it as some flow. So because the shear stress is flowing, so we call it as shear flow. Or we can say that the shear force is flowing. Shear force is flowing. So then after that, in the vertical direction, we say there was some based on this cross section, yy cross section. This was your cross section yy. You would be having some shear force diagram. So some shear of v is acting here. Some shear of v is acting here. So we can show that there is some shear acting. So then after that we show that the flow flows that the flow would be in this fashion. That this is some flow. This is some flow. Based on this flow, like a liquid, we can say that continuity must be satisfied. Continuity must be satisfied. I can say continuity of shear flow, continuity of shear should be satisfied. That should be satisfied at the junction. Say if from the side some shear, we call it as shear flow is acting. Shear flow is coming to the junction, and from the side there's some shear flow acting. So on the web side we should have some 2q naught entering the junction into the web. Similarly, once it reaches to the top, it should give the same value of shear flow. We should verify that. We should verify that. So your shear flow, actually we have the shear stress equals to some balancing horizontal shear into thickness into, we can say, thickness into small differential element dx. So we have that shear. We say that if the shear force is if you talk about that shear force along the longitudinal direction, so per unit length dx, that we call as tau b, and that's what we call as shear flow. So we can say your shear flow is the shear force per unit length. If you take per unit length of, let's say, dx equals to 1, a unit length of that x equals to 1, or then we say that the shear force developed per unit length, it would be your shear flow. So the unit would be kilonewton per meter for the shear flow. So the equation we got, tau times b equals to shear flow. Now one more thing is that let's take that case of I section. Want to say whether this continuity is balanced. So want to say whether this continuity is satisfied. So let's write that shear stresses in. We already solved problems, but that was based on those values of that. So want to say I want to take a general picture of that shear stresses in the I section beams. Let's have that. Let's have the cross section. Let's take the cross section. Let's have the cross section. So you got this I section. Now we are saying that let's call it as a thickness of T, and same thickness of T here, and the thickness of web is also thickness of T. And we say that the center to center, let's forget that center to center. Let's say that the thickness of the web, we call it as small d. Let's say this is the small d, and the total depth, we call it as a capital D. So total depth of the section is d, and we can say that d equals to d plus 2t. And if you want to say what is the value of t, and value of t would be equals to d minus d by 2. Can you say that? Let's say this is the neutral axis. If you want to say what is the value of t, that would be d by 2 minus capital D by 2 minus small d by 2. So your thickness would be equals to d by 2 minus d by 2. Then after that, let's call the width as b. Now we want to say what is the shear stresses on different. We already know that the shear stress diagram, we know that would be in this fashion. We already calculated. We solved 2 problems on that. So we want to say what are the different values in terms of general a general equation. What is this value? What is this value? And what is this value equals to? Want to say what are the different values here. Now let's calculate those values. So let's take the first part, that is, we want to say what are the shear stresses in the, let's say, first part. We want to say shear stresses tau in the flange. We want to talk about the flange. So if you take that flange, if you take out that flange, let's take that flange. So you are taking that flange. So let's take that flange. Let's say any point A. Let's call this point A. You take from the neutral axis a point A at a distance of y. So we want to say what are the shear stresses in the flange. So the shear stress equation says that get the area above that point A. Let's say this is the point A. The area above that point A, that is this small area, and we'll call this area as A area A dash. Let's call it as area A dash. We want to say what is the value of that area A dash. Can you say what is the value? Can you tell me what is the value of area A dash? Total depth of D. This value is d by 2, and this value is small d by 2, and this is thickness, and we want to say what is the value of this small area. I would say that equals to some width b times small thickness of this one. So I would say that value of this thickness would be equals to total is d by 2. Total is d by 2 minus y. Yeah, total is d by 2, and you subtract minus that, subtract y, and you are left with this part. So d by 2 minus y. And you want to say where is the centroid of that area acting? So centroid would be acting here. So what is the value of this part? So I would say out of that smaller depth, this depth, it's acting at 1 by 2 of that. It's acting at 1 by 2 of that plus your y value, plus your y value. So your centroid is acting at y. I would call it as y bar is acting at y plus half of that d by 2 minus y. So you got the y bar also. Now if you use the shear stress equation, tau equals to v, then v a y bar and divided by some, there would be some moment of inertia. We don't worry about that moment of inertia. That we keep the equation in terms of that I neutral axis. That would be some value of capital B d cube by 12 minus this thickness minus, if you subtract b minus d, then you are left with that thickness. This you subtract this part, then you are left with b minus d. Then depth, the total depth would be left over d cube by 12. B d cube by 12. B d cube by 12. D minus 2t by q. D minus 2t, or we can say d cube by 12. Yeah. So we got this, but we are not worried about. Let's call it as I. And after that, we are talking about the flange. Let's call it as shear stress in the flange. We are calculating the shear stresses in the flange. There the width at A, we can call it as width at A, that is itself equals to B. So this is what the equation we got. Then if you simplify it, we can write it as V by I d by 2 minus y times 2y plus d by 2 minus y by 2. Yeah, 2y plus d by 2, yeah, divided by 2. So we got this value of v by 2y, and we got this equation 2y minus y, that's y. So we got a plus b, a minus b. Then we can write d squared by 4 minus y squared. So we got this general equation of that shear stress in the flange. V by 2y d squared by 4 minus y squared. Okay. Now, if you want to take that at the junction value, that if the y goes to the junction itself, that if the y goes from that 0 to d by 2, if the y goes to d by 2, that is the junction between web and flange. Let's write that if tau at flange at the rate of y goes to d by 2, want to say what is that value equals to? That is d squared by 4 minus, that is d squared by, yeah, that is small d squared by 4. That is small d, that's also d by 2, small d by 2. Your y value is d by 2, small d by 2. So you got the value of, you got the shear stress value. Shear stress value equals to tau at the junction, shear stress in the flange, but in the junction part we have that equals to v by 8i d square minus small d square. So we have this equation. Now let's make that I section. Let's make that I section. Let's say this is some I section. So I would say on that junction, but in the flange part, we have some value of shear stress that was equals to v by 8i d square minus d square. So we got the shear stress value here. Now we want to talk about the shear stresses in the web part now. Well, we are worried about the web part now. Let's take that web part now. Let's talk about the web. let's talk about the web. Let's say this is some web. So let's say this is the web, this is the flange. So let's take any point. Let's call it as point A. Let's take any point A in the web, at a distance y from the neutral axis. So this is some point A, and we want to say what is the shear stresses at that location of A, but it is in the web. Shear stresses at that point A, but it is in the web. So you need to take that from the equation, you need to take the area above that point A. Let's take the area above that point A. So that point A, at the point A, the shear stress at the point A is contributed by the area above that point A, So let's have that. If you calculate that summation of AY bar, because we have two area and we have two centroids, so we can calculate first moment of area. So one area is here, it's centroid somewhere here, and second is centroid acting somewhere. And we have this value of d by 2. We have this value of d by 2, and we have this value of capital D by 2, and we have this thickness of T. So we want to say, can you tell me what is this value? This value is equals to d by 2 minus y. So if you take first area, I would say the first area equals to d by 2 minus y into width of T into that thickness of T. This is thickness of T. So we got the first area, and its centroid is at a distance of y plus 1 by 2 of d by 2 minus y. So I can write that also. Y plus 1 by 2 of d by 2 minus y. So we got the first moment of area of that particular first area, I would say. Then second area we have that equals to some b into t, and the centroid is at a distance of some d by 2 plus d by 2. That is this value, d by 2 plus d by 2. I can write d by 2 plus d by 2. Now we have to convert that t. We know that t value equals to d minus d by 2. We have that t that equals to that this minus, we have that d by 2 equals to that, we have that thickness t that equals to d by 2 minus small d by 2. So let's convert that in terms of that d and small d. So we are left with d by 2 minus y into some value of d by 2. We can write in this way, and then substitute the value of t also. So we got this value of 2y plus d minus y divided by 2, and you have also d by 2 here. So we got this one, then plus b times and thickness, that is d minus d by 2. Then after that d by 2 plus 1 by 2 of d minus d by 2. So you got this equation. So you have to solve this one. You have to solve it. So we got this. If you see this part, this is 2y minus y. That's net value of y plus d by 2, and we have this one also. So a square minus b square. So we can write d square by 4 minus y square. We can write that d square by 4 minus y square, and we got this one also, d by 2 by d minus d by 2, and we have one more d, that 2 value downwards, so we can write d minus d by 4. And for the next part, you can have that b into d minus d by 2. Then you solve this part again, so that we can take 2 common. Finally you got d minus d by 4, and you can take d plus, you can write 2d plus d minus d divided by 2. d minus 2d plus capital D minus small d. So you got this one. So you can write 2d minus d, that is equals to d. So you can write d plus d and d minus d. So finally, equation of d square minus small d square divided by 8 b times. So you got this part, and we got the first part. So you can write the final value, that we have the AY bar equals to d square by 4 minus y square into d minus d by 4 and plus b by 8 d square minus t square. So you got the first moment of area. You got the first moment of area. You got the first moment of area, d square by 4 minus y square, b by 8 d square. Yeah. You got the first moment of area. And I you can keep the I as it is. Now you would say that what is the value of shear stress now? What is the value of shear stress now? So I can write shear stress tau in the web at particular location of A, that equals to V a y bar divided by I into thickness in the web. Thickness, so your B at A should be equals to thickness in the web, that is the thickness of D. So it would say, what is the thickness at that point A in the web? I would say that thickness equals to T. So that equals to T. So you can write IT, information technology. So IT, you got the IT. Now you have to substitute this value. You have to substitute this value now. You have to substitute this value now. So this value you have to substitute here. You have to substitute this value. So if you write it, so we got this value V by IT and into your d square by 4 minus y square and your d minus d by 2, d minus d by 4 plus b by 8 d square minus a small d square. So you got this value V a y bar by IT. That's your shear stresses at that location of A in the web. Now if you simplify it again, so you got this shear stress. Now if you want to say what is the value, if you take that T also here, we have this T. If you want to say what is the value of shear stresses at the location of I would say at that junction. If you take the shear stresses at that junction, but in the web, at that junction, that means at the rate of where you have to go. You have to go to the junction. That means at y equals to d by 2, at y equals to d by 2, you have to see what is the value of shear stresses in the web part. At tau equals to, I can write y equals to d by 2. If you substitute here, and thickness we know that this thickness value of t equals to d minus d by 2. So that if you substitute that also here, so you can have that also. So if you write d minus d by 2, similarly if you take that d inside, if you take this d inside, so for the next part you can get b by t, and in the first term you can get one more term, that's 1 by d minus d divided by 2. You can get this one term also int. So finally this part goes, and this part goes, and you are left with only 2. So you are left with this part only. So you are left with this part. And for the next part, you are left with b by t, b by 8t, d square minus d square. So you got this one. Now if you substitute the value of y equals to d by 2, that means your shear stress would be equals to v by I, d square by 4 minus d square by 4, then plus a b by 8t, d square minus d square. So you got this one is 0. So you are left with final value of that shear stress in the web part would be equals to V by I, then B by 8t d square minus d square. So you got this part. You got this part now. Yeah, you got this part. So if you substitute this value in that variation of shear stress, let's have that shear stress variation that we have already plotted some part. Now after that we have to check what is the value of shear stress just at that junction, but in the web part. So there is some value that we calculated as V by I 8 b by t d square minus d square. That's the same value we got for the flange, but we have some factor of b by t, because your thickness goes decreasing in the web. Because your thickness decreases in the web, that means your shear stress would increase. by an amount of thickness in the flange, width in the flange divided by width in the web. So this factor we have to multiply it for the first part. So there is some raise. So we can call this final value of v by 8i d square minus d square into b by t. So we got this value, final value of v by 8i d square minus d square into b by t. Now you want to say what is the value of that shear stress at the mid in the web. So I want to say what is this value at the neutral axis. That's at y equals to 0. At y equals to 0, if you substitute that in the equation, we would say what is the value of that. So if in this equation we substitute value of y equals to 0, let's substitute value of y equals to 0. Let's substitute the value of y equals to 0. Let's substitute the value of y equals to 0. That means tau at neutral axis or tau at the rate of y equals to 0. That means that is equals to v by I d square by 4 d square by 8, and this is 0 plus b by 8t, then d square minus d square. Initially we had this part. Now we have one more extra part, that's d square by 8 into v by I. d square by 8 into v by I. So we got this extra part of vd square by 8i. We got this extra part of vd square by 8i. So we got some extra part of vd square by 8i. This is some extra part. Up to this point there is same value from the junction to that neutral axis. We got the same value, but after that we got some increase. We got some increase also, that vd square by 8i. So let's have from this side also some variation of shear stresses, some shear stress variation. So this is your final diagram. So the condition is that you should have a symmetric eye section. That is, thickness of the flange should be equal to thickness of the web, and you should have symmetric cross section. That means neutral axis is at the mid. So you got these values then. So here the value we have, and same value is we have in the web part also, but you have to multiply that factor b by t. Then there is an increase from the junction to the neutral axis, that is equals to vd square by 8i. So you got this shear stress variation. Now from the shear stress variation, we had that the initial topic we had that we said there should be some that the continuity of that shear flow should be satisfied. If there was some shear force Q0 entering the junction from the both sides, that's 2 Q0, that should be equals to the we want to check that whether that Q2 Q0 is entering the that flow in the web also. Is it equals to shear flow in the web also? We want to check that out now. Based on this derivation of shear stresses, based on this distribution, based on this variation of shear stresses, we want to check now whether that continuity is satisfied or not. So let's remove this part now. Let's calculate now. I would write now topic of variation of shear flow. Right, variation of shear flow. Variation of shear flow. So we have two directions. One is your horizontal, I can say one is your horizontal direction. Next one is your vertical direction. That shear flows in the horizontal and it flows in the vertical. We want to say, let's talk about the first case, that is your horizontal shear flow. Let's talk about horizontal direction. So first one is your horizontal direction. So for the horizontal direction, you need to take that variation of shear stresses in the flange, because horizontal variation of shear is in the flange. We know that horizontal shear is in the flange. Based on that, we said that shear flow is in the horizontal direction. So in the flange, you have horizontal variation. We want to say what is the variation with the change in that width, with the change in width. So let's have that. If you use those values, of shear stresses we got, we got the shear stresses values. So similarly let's have that in the horizontal direction. We can write This is your I section. This is your I section. From the neutral axis, you take some point, you take some area of thickness t and some width in the z. So this is your z axis. We take some width of z, and total width is b, we know. And we want to say what is the value of shear stresses at that point A. Let's say this is point A, or we can say this is point A and the centroid is here, somewhere here. Let's have this point A here, and I want to say what is the shear stresses in this part of the area. So I would write that shear stresses at that location of shear stress would be equals to shear stress in the flange equals to V a y bar, the value of A equals to z into t, a y bar value of y bar value would be equals to y plus t by 2, y plus t by 2, and after that divided by I into your width. What is the width at that location? What is the width at that location? That width at that location, while you are calculating the shear stresses, that is equals to b, that equals to some value of b. So one more thing is that, but if you talk about shear flow now, you have to say some shear stress into some width of b. That is your shear flow, and that would we get a value of shear flow equals to vzt y plus t by 2 and divided by I. So we got the shear flow, and we want to say at if the z value is 0, from the z, if the z value is 0, if substitute value of z equals to 0, so you got a value of 0, shear flow at z equals to 0. So shear flow equals to 0 at the end, and so we got a shear flow is a linear variation of z. So shear flow is a linear variation of z up to the mid part, because from the both sides we have some shear flow. If you go up to the mid part, that is at b by 2. If you substitute that at b, at z goes to b by 2. If you write what is the value of shear flow at the rate of z goes to some b by 2, so you get some value of shear flow that's equals to vb by 2 into thickness of t into y plus t by 2 by I, and that we call as q naught. Let's say this is some value of q naught, and so that we say there is some linear variation up to the width b. There is some linear variation of shear flow. There is a 0, and this is some value of q naught at the mid. This is some width of b by 2. So we got this variation of shear flow. Linear variation in the horizontal direction, I can say, in the flange. So if you substitute the value of t, let's substitute the value of t, vb by 2, thickness of t, that's t minus d by 2 into y plus d minus d by 2. You have already 2 there, so it becomes 4 and divided by I. So you solve it, we got vb by 2 to the 4, 4 4s are 16 I, and you got d minus d, and you got 4y plus d minus d, 4y plus d minus d, 4y plus d minus d, 4y plus d minus d. Yeah. Now the thing is that you see from the neutral axis you go to some point value of y, but what was the value of y? What was the value of y? If you have this value of y, what's this value? That you go to the point A that was at the bottom of that flange, so your value of y would be equals to d by 2. So your value of y equals to d by 2. So y value of d by 2. So y value equals to d by 2. We write that y equals to d by 2 because we have y equals to d by 2. From this one, we have y equals to d by 2. If you substitute here y equals to d by 2, that means we got 2d minus d. So we got finally 2d minus d, that means d plus t. So we got equation of d square minus small d square, and vb by 16i, that equals to some shear flow of q naught. So this is the shear flow. We can write this is the shear flow this is shear flow from one side, on one side of junction, I can say one side of junction. From the one side of junction in the flange, we have the shear flow coming to the junction. So shear flow of that Q0 is coming to the junction. This is some junction J, and there would be some one more Q0 entering from the other side of the flange into the junction. So from the junction there should be that 2 Q0 going downwards, and we want to check whether this is satisfied from the shear flow in the web. We want to check what is the shear flow in the web. Based on the equation we got for the shear stresses in the web, we want to say what is the shear flow in the web. Now similarly, if you want to say what is the vertical variation, we got the horizontal variation, that shear flow variation. You can say this was your flange, this was your web, and this is flange. We can say up to the junction there is a raise of that shear flow, that horizontally, that in a linear fashion from 0 to Q0. And similarly from the other side you can say there is some linear variation Q0, and you can make the final diagram. I can say this is the linear variation of Q0. That's horizontal shear flow variation, horizontal shear flow variation. Or you can say in other perspective you can draw based on the direction. You say that this is the shear flow in positive x direction, and this is some shear flow in the y that negative x. And then accordingly you can say, let's say this is some positive Q, and accordingly from the bottom side you can draw in this way. Let's say this is some Q and this is some Q. So this is one more representation of shear flow. That means the linear variation is there, 1 degree variation, linear variation. With the width, with the z, you go to the value of z from 0 to b by 2. So there is some variation of shear flow in the horizontal, that is a linear function of b, or we can say z. So you got the shear flow variation in the flange. Now you want to say what is the variation in the vertical. Now we are worried about this part. We already know that the shear stress variation is parabolic, and we want to say what is the variation of shear flow in that vertical direction, in the depth of that, we can say in the web part. Let's have that part. We already calculated that. Let's have the second part. We can write the topic of second part. That's called as case B. That's vertical variation of shear flow. I want to say vertical direction, how the shear flow is varying. So second part. Now for that you had to take some element. In the web. You have to take some element A in the web. Then you take the area above that point A, and you calculate the shear stresses. Thereby you calculate the shear flow. We already calculated the shear stresses in the web at a particular location of y from the neutral axis. So we already calculated the particular shear stress equation in the web at particular location of y, and if you multiply with that the thickness of the web, you get the shear flow equation in the web. So you already have that equation of that shear stress. We already have that equation. See, we already had that equation. This is some equation we had already. This is the equation we already have. This is the shear stresses at A in the web. That is this one. And if you say what is the shear flow in the web, that is shear stress in the web into the width of that. That is thickness of web, that is T, because the thickness in the web, that is T. So you multiply it here. So we got a value of shear flow equals to V by I, and then D square by 4 minus Y square, and divided by 2, and you multiply it with the thickness of T, and plus you got your T here and T here on the top, you got cancelled that. So you are left with B by 8 D square minus small d square. So this is your variation of shear flow. Now you got this variation of shear flow. If you substitute the value of T was equals to D minus D by 2. Let's have that also here. So now you apply the limit that if the shears, you want to say what is the shear flow in the web, but at the rate of junction, that is when y was equals to d by 2, when y is equals to d by 2. So if you go to that point, let's go to that point. So you had some point A. See here, you had some point A. You want to say what is the shear flow at that junction? That means at y goes to d by 2. If y goes to d by 2, you want to say what is that value of shear flow? If y goes to d by 2, that means q in the web at junction, that equals to v by 2i and d squared by 4 minus value of d squared by 4 also into d minus d by 2, then plus b by 8, then d square minus d square. So you got some shear flow value of, this goes to 0, so we got value of v by 16i d square minus d square, v by 2i v by 2i. So we got this one. Is this equation correct? That shear stress equation was equals to v by 8i. The equation was v by 8i. So you have this equation, v by 2i. Okay, v by 2i d square minus d square. This part is correct. And after that we had the equation of v by 8i. Actually it should be, there was this part. It was actually, we had this equation. This should have been from the, during the derivation we had, it should have been this one. It's that two you don't have to take common. You don't have to take common here. This was for the first part. You can have that 2. You can have that 2 for the first part. For the second part, you had only that 8 value here. You don't have 16 here, so you have only 8 here. So if you only have 8 here, that means this 2 was not common. And this was in the first term itself. That value of 2. This was in the first term. This was not outside. So you got final value of v by 8i, that shear flow in the web in the junction, that is equals to v by 8i d square minus d square. So we got this one. There was some correction. It happens that there was some correction error. I would say correction was there. This should not be outside. This was the term with the first one. This was the value of 2 with the first term, that 2. So based on this calculation, we had shear stress in the web, that is v by 8i and d square minus d square. So if you check that, what was the shear stresses at the junction, shear flow in the junction, but from the top side, that is from the flange side. From the flange side, if you say what was the value of shear flow, from the junction, from the top side. So this was your shear flow from one side of junction entering into the junction. So I can say this was some shear flow of Q naught entering the junction from one of the sides. So it entered a value of Q naught, that is this one, and similarly there would be one more Q naught entering from the other side. So I can say final Q 2Q naught would be equals to, VB by 8i, that is d square minus small d square. So you got this value of shear flow entering into the junction. So that means same value should enter into the web. Same value of 2Q naught should enter into the web. And we want to say whether our equation was correct or not, 2Q naught. So if you analyze those two values, and that means your Q in the web, that should be equals to 2Q naught. And that is satisfied. That means continuity of shear flow is satisfied. Continuity of shear flow is satisfied. So we got this one, and we know that the variation we can say, if you now have that variation of shear flow, I can show that also. So For the horizontal we got, for the flange we know the variation. Now we are talking about that web. So we got the variation on the top. We can say the top variation would be, either you can show in this way, Q0 and Q0. Similarly, from the bottom side also you can show Q0 and Q0, Q0, Q0. But for the horizontal, you can say at the junction we have some value of that is 2Q0, and from the top side also we have some value of 2Q0 entering into the web 2Q0. This was Q0, this was Q0, and enters a value of 2Q0 into the web. It enters the value of 2Q0 into the web. Then after that there was some linear variation of y square, that parabolic variation of that shear flow, because the equation was in terms of y. If you see the shear flow variation, it was in terms of y square, so we can say that the variation would be in terms of y square, so a parabolic variation would be there up to the neutral axis. So this is our shear flow variation in the web. So your final conclusion is that the horizontal shear flow is a linear variation, and in the vertical shear flow variation is quadratic parabolic variation. This is the crux of this derivation. So we got this one. Now one more thing is that we had this cross section. Based on that unbalanced bending forces, Fxx and Fyy, we said there's some shear force F shear, and based on that we said there's some tau xz into dx into b. So there's some shear stresses. That means on this side there was some shear stresses along that flange. So that means there would be some shear stress in this part also. So if I take any element of dA in the web, in the flange, if I take an area of dA and I say that there's some shear stresses on this part, there's some shear stress of tau zx on this part, and for this configuration I can say summation of horizontal forces in the z direction, because this is your zx. I can say summation of horizontal forces in the z direction should be equals to 0, because there is no load. That means it should balance itself. I can say tau xz, that is, there is some small differential force. There's some differential force, and there is no other force in the horizontal. There is only a tau zx on those differential elements. Tau zx on those differential elements. If you take that integral for the entire area, there's some small tau zx also in the web, but we ignore that. This part we ignore, and we said for the entire area, if you integrate it, that should be equals to 0, because your horizontal force in the section should be 0, because your equilibrium should be satisfied. That's our job in civil engineering. That's that equation of statics, that to have that every structure, every element to be in equilibrium. Then if you say that summation of forces goes to 0, that means since we can have one point that tau xz is not 0, it can't be 0, because of complementary shear stresses. If from the other side of the flange, because of unbalanced bending forces, you had some tau xz, that means there should be definite tau xz. Yeah, there should be some tau zx. This was your tau zx, and this is your tau xz. There should be some tau xz. So how can this be possible, that shear stress, that overall value should be 0, but area can't be 0? Then we can say, finally we can write, which implies that there should be some average shear stress and into some area that should be equals to 0. That means some average shear stress would be 0. So we got this one, that average shear stress in z direction is equals to 0. It's not that shear stress in z is 0, it means average shear stress would be 0. That means if there was some shear stress in this direction, and in the opposite would be some shear stress also. Similarly, from the top, if there was some shear stress in this direction, there would be some shear stress in the opposite direction. Okay. Now, if you talk about that, if you say that this is some element, this is some element A, B, C, D, I would say your tau xz is significant in the flanges, we can say. Significant in flanges, but negligible in web, because you have less thickness here, we have here that we have that tau dx into t, or width. We have less thickness here, so your shear force contributed, we can say tau xz is less, it's negligible in the web. But if you talk about the tau xy, this is tau xy, this is tau xy, that is significant in the flange, in the web, but we can say negligible in the flanges, because for the flanges you have, if you have some shear stress tau xy, that means your thickness is very less. If you analyze this, it's not that thickness is this much. If you say we call them as the thin member structures, or we can thin walled members, we call them as thin walled members. The thickness is such that it's very less as compared to the other dimensions. So they act as a flats. We call them as a flat section also. That if you have this section, if you assume that this is some flat section, this is some flat section, this is some flat section, and the length is very much, and the width is also very much. So this, you can say this is very less thickness. We call them as thin walled members. Similarly, this one, we have this web. This web looks like this one. This is some thickness of t, and this is continuous for a length of, say, some meters, and depth is also some 1 meter, let's say. So your thickness is very less. It's some 1 mm, it's some 10 mm, let's say. It's some 10 mm. So thickness is very less. We call them as thin walled members. And if you say what is the value of shear, stresses in this one, in this I can say tau xz, that's very less, because your thickness is very less. And similarly, if you say what is the value of shear stresses in the flange, that's tau xy, I would say this is very less. But for the shear stresses in the web, that's tau xy, that's very much, because your thickness comes very much here, because your thickness is very much. So your thickness of that's equals to some depth, small d. Your shear, I can say your shear stress is parallel to the surface. Shear stress is parallel to the surface. You can't say this is this one that perpendicular. It's parallel to. That means your shear stress is acting in this way. Shear stress. So more length you have, that means more surface you have, that means more shear stresses would be there. So you got this. Now we can say if the shear stress is parallel to the surface. Now if you have a circular section, I can say thin walled circular section. If you have this thin walled circular section, let's say there is some circular section of that thin walled. I will write as a circle, and after that you have one more. Let's say this is your thin walled circular section, and how should be the shear flow variation? And we say that the shear flow variation should be shear. I would say shear flow is parallel to the surface. For the circular member, we can say that is tangential. Tangential to the surface. If you draw tangent at every point on the surface, I would say this is the shear flow variation. This is the shear flow variation in the thin walled circular members. This is the Q variation, and Q would remain always constant. There is no Q changing. So Q is always constant. At every segment we have Q constant. So Q is constant always for them. So we got this part. If you want to take a few more problems, if you want to take few more variations, let's say we have this circular. You can also show that based on the depth, we say that shear stress would be 0 here, and maximum it goes to some value of shear stress, and similarly from the other side. So this is some variation. And if you have that same circular section, but there is some slit, that there is some opening on the side, from one of the side of the periphery, I can say from one of the side we have this part that is opening. We call it as an opening or a slit, 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 whatever, slit, that's opening. We have some opening. So the shear flow variation would be some sort of in this way. Let's say this is some shear flow variation. So based on this, we say this is some variation of shear flow or shear stress. This is some variation. So you got this one. After that, we can take box section. Let's say this is some box section, thin walled box section. The thickness is very less. So this part we have only. This is free, or we can say this is open. If I want to say variation, if we take the variation, I would say the variation would go in this way. Because your shear flow would be in this way. We know that shear flow variation would be in this way. Based on this fact that when you take differential element, when you took that differential element, you said there is some unbalanced horizontal force, then there came the tau xz. Similarly, you can have that tau xz from tau zx from tau xz from this other side. So there would be some shear flow again. Q. So based on this, we can say there is some flow. And similarly, you can have in this way also. You can have this way, and for the depth, we can say this is some value of 2q, or we can say this is some value of because see for the I section, we had this variation of q and q. We said this is q and q. Finally, the value here, we said that value is 2q because the 2q is entering into the junction. And because we have only one member here, that's a one web we have. So based on that, we said there is 2q shear flow here, and then it goes to some value maximum. But here we have two sides. We can say there are two webs. We can say there are two webs. We can assume that there are two webs. So we can write then only q enters one. Then after that it goes some variation. There is some q. Then it goes some variation. So similarly, from the other side, you can say there is some value of q, and there's some value of q, and it goes some variation of parabolic. And one more thing is that if you take that channel section, I would say there is some variation of shear flow. You can show in this way, or you can show in this way. So you have this value of q and q from both sides, and similarly we have two. We can assume that we have two webs. Then we can show the variation that this is some value of q, and it can go to some value of max. Then it goes to some value decreasing. Similarly, from this side, so you can have some value of q, and then it goes to some value of maximum. Then it goes to 0. And from the top, we have this variation. So this is some shear flow variation. This is the variation of shear flow. So we got this, and one more we can take. Final we can take that you have this section. We have this section. We have this section. We know that for the vertical members we have the variation of that parabolic variation. There's some parabolic variation, and it goes to some value of max, that is q. Let's call it as q naught, and same will enter into the flange. We can call the horizontal members as flange. So based on that, we can say there is a continuity. I would say if the q naught enters here, there would be some shear flow here equals to q naught, and it would increase to some value of q1. And then after that we can have that, since see how this why I can say why q naught is not equals to q1. Why? See, q naught enters up to this point. After that, we know that variation of shear flow in the horizontal, that is a linear function. That is some linear function. Had it been 0, had this part been not there, so your variation would have been some value of QA, but because your variation is already there, we have already accumulated value of Q0, so then if after it would increase after that from Q0 to some value of QA, such that overall value becomes Q1. So finally Q1 enters to this part. Finally Q1 enters here, and we can say this is vertical member, so we can have parabolic variation. Let's say there is some variation of parabolic, there is some parabolic variation such that here we can have one more value. Based on the symmetry, we can say maximum value we can have up to this point, and after that we can go again to the value of Q1. We can again go to the value of Q1, and after that from the bottom we can say there would be some shear flow in this fashion at that this is a parabolic, this is some parabolic variation, and this value would be equals to same value of Q0. This is also Q0, and here would be some variation of linear variation from Q1 to Q0. So this is some variation of shear flow. You have to ensure that continuity of that shear flow. That should be satisfied, that continuity. Based on that continuity, you can draw that diagrams. You can draw the diagrams, and once you know the variation in the horizontal, and variation in the vertical, you can draw the diagrams. In the horizontal you can have linear variation, and for the vertical you can have a parabolic variation. So this is very easy. If you use these three tools, that in the horizontal you have linear variation, in the vertical you have that parabolic variation, and at the junction you have to ensure continuity. At the junction you have to ensure continuity. Continuity. You have to ensure continuity. So once again I can tell you that, see, on the free surface we have shear stress 0, so I can say shear stress would be 0 and shear flow would be 0. Then in the vertical members we have parabolic variation, and it goes to maximum value of Q0, and after that that same value would enter into the junction. That Q value, it enters to the junction. Thereafter we have a horizontal member, we can say horizontal member. Then in the horizontal member there is a linear variation. It would linearly vary from Q0 to some value of Q1, such that maximum value, net value is equals to Q1. We can write QA plus Q0 equals to Q1. Let's say this part is equals to QA, and we can have this Q1. Finally the same value will enter here. Let's say this is some value of Q1, and after that in the vertical members we have parabolic variation, but based on the symmetry we say from the both sides we can have same parabolic, that we have same nature of that diagram. So you can draw that same diagram again. So one more point is that if you have doubly symmetric thin-walled sections, thin-walled sections, or we can say thin-walled sections. So let's say this you have a section such that it's having two principal axes. We can say if there is one principal axis along which that product of inertia equals to 0, that's a principal axis 1, or we can say one axis of symmetry. We have one more axis of symmetry. If the load passes from the centroid, and this is your load, if the load passes from the centroid, but you have two those axes of symmetry, then one thing is that you have to resolve your force in z and y direction. You have to resolve it in z and y direction. Accordingly, you can get some component. Then after that, you can calculate the shear flow in the both directions. Then you do algebraic sum. You get value of Q1 and Q2 at any location of I, at any I location where you want to find shear stresses. So you got the value of shear flow at that location of I1, and similarly QI2 shear flow of 2, but at ith location, and you do summation of those two shear flows, QI1 plus QI2, based on the continuity equation, and you can get the value of resultant Q. Then after that, if you want to say what is the shear stress at that location, you can say your shear stress would be equals to that resultant shear flow at that location into some width at that location. Yeah, divided by the width at that location, the thickness. This is the thickness at that location. So we got this. If you have we have one more that smaller topic, that's the variation of shear stresses in other sections. We have already shown you that some examples. Let's say variation of shear stresses for some other sections. We have that if there was rectangle, we have this variation. If there was circular, we have this variation. If there was triangle, we have this variation. If there was diamond, we have the variation of some value of some sort of b was there. Some sort of b was there. This was some variation. Then now if you take that, we have I section. We have I section. We have this variation. I section. We have this variation. We have this variation. Now if you take let's take the H section, I can say. Let's take the H section. Let's say this is the H section. I would say along the depth there is a parabolic variation, but as long as it reaches to this point, there is an increase of depth. If the depth is increasing, that means the shear stress would decrease. So shear stress would decrease. So the shear stress would decrease. Shear stress would decrease. But after that, we know that as we go towards the neutral axis, your shear stresses would increase. Then after that, it would increase some value to some value. That's tau neutral axis. So you got this variation, and this value, this variation is same for if you have one more section, that we have plus section. If you have plus section, you can have same variation. Let's say this is some plus section. If you have plus section, you can draw the same variation. And one more, if you take one more, that if you have T section, it's very easy. Based on the I section, you can say T section is also easy. There would be some neutral axis somewhere at the centroidal axis, and I would say there is some variation. Then after that, there is a change in width thickness. Then that means your shear stress would increase. Then after that, it would go to some value of max here. Then I can say there is some variation of parabolic, so it's your variation, shear stress variation. Now if you have that rectangular section, but you have cut the mid part, this is open, so we have only this part now. Your solid part is only this one. So if you want to say what's the variation, I would say had it been rectangular section, I would have drawn in this fashion. So I would say after this point we can have this variation. Then after that we have decrease of thickness. Thickness decreases, that means shear stress would increase. That means shear stress would increase. If the shear stress increases, so similarly from the both sides we can have that shear stress increases. Then after that it can go to some value. So this is your variation. This is some variation. If you take that, finally, that we call it as a built-up sections. That means if the section is such that if the load was such that your I section was not sufficient, that means you need some extra plates or extra members to connect it with it. If you connect a few members again with this one, let's say you connected some angle section, you connected some angle sections. Let's say this is some angle section. So you got this one. Now we have different points. Here. We know that variation for the that I section is in this fashion. It is for the I section. But we have few angles also here. We call them as angle sections. We call them as angle sections. This one is your angle section, and this is your I section. And overall value is, we call it as a built-up section. So let's have that variation. So here the shear stress is 0. Then it goes to some value. Then after that, it would, since your thickness goes to decreasing, so your shear stress would increase. Then after that, what happens? After that? As long as you reach it to this point, your shear stress would have been in this fashion, that it goes some parabolic variation. But now your thickness goes again decreasing. That means your shear stress would again increase. Similarly, if you have this variation, you can say there was some increase. After that, there would be some sudden increase again. So after this point, there is some variation. Parabolic variation. After that, area is only this part, we can say thickness is this part, final thickness, so there would be some increase again. So finally you can say after the neutral axis we can have maximum value of some value of maximum. This is your variation, shear stress variation. So this was the end of the shear flow. Hope you enjoyed the lecture. Thank you for watching this concept of shear stresses and the shear flow in the section. Thank you for watching.